All right, so here in problem 30, we have a problem. We're trying to predict body fat percentage from their weight. So we see a kind of a moderately positive trend there. It's definitely straight enough. If I go to residual plot, it's scattered. The residuals are roughly unimodal and symmetric, and the normal probability plot is fairly straight. So we're going to do a hypothesis test in a confidence interval here. So here's what we're going to do. The parameter here, big B, is the linear relationship between body weight in pounds and body fat percentage. Alright, so that's our deal. The null hypothesis is that this is the null. We can do that over. The null hypothesis is that big B is 0. The alternative is that big B does not equal 0. Okay. So the assumptions, if we look at this, okay, our scatter plot is definitely straight enough. Our residual plot does not show a pattern. Our histogram is roughly unimodal and symmetric, and each person's body fat and weight are independent. So we're going to list those down. So the scatter plot is straight enough. The residual plot shows no pattern. The histogram of the residuals is roughly unimodal and symmetric. Okay, and then each person's body weight and body fat percentage is independent. Name the test. This is a linear regression t-test. Test statistics. So let's see. N here is 20. That's right here. Okay, degrees of freedom is 18. B sub 1 is I'm just going to say 0.25. Standard error is 0.06065. Okay, and then I'm going to write the linear regression line. So our y-intercept is negative 27.4, and let's see, it's going to go up by 0.25 per pound. Okay, so that's basically the explanatory variable and the response variable. So the obtained P, T equals B sub 1 minus big B over the standard error. And if we look at this, if we do 0.25 divided by 0.06065, we get a t-value of 4.12. So now this one's going to be a little bit different because it's a two-tailed test, right? So our p-value is 0.0006. It's right here, but it's a two-tailed test, so our p-value is really 0.0012. We got to double that 0.0006. So p is 0.0012. Okay, so we make a decision, and in this case we're going to reject H sub O at the 0.05 level. And our conclusion is, since P equals 0.0012, there is strong evidence of a linear relationship between body weight in pounds and body fat percentage. Okay? And then what we're going to do is, what's our R squared? We go over here. So R squared is 48.5%. So R squared is 48.5%. So 48.5% of the variation in body fat percentage is explained by variation in body weight in pounds. Then we're going to get our R value, so we take the square root of 0.485, and it's about 0.7, so R is about 0.7. Alright, so there is a moderate positive linear relationship between body weight, and I'm going to put in pounds, and body fat percentage. Okay? And then we're going to do a 95% confidence interval. So the confidence interval equals B sub 1, which is 0.25, plus or minus t. Now we got to do a t value. So I'm going to do a 95% since we did a two-tailed test. So we start at the 2.5 percentile, we end at the 9.975. So I'm going to do inverse t, 0.975, and how many degrees of freedom? 18, right? And we get 2.1. So we're going to do plus or minus 2.1 times the standard error, which is 0.06065. So I'm going to do 0.25 plus or minus 2.1 times 0.06065 is 0.127. Okay, so 0.127. So 0.25 minus 0.127 is 0.123, and 0.25 plus 0.127 is 0.338, 0.377. Okay, so here's the deal. We are 95% confident that as a person's weight increases by 1 pound, their body fat percentage will increase between 0.123, so that would be what? 0.123% and 0.377%. So as one person's body weight goes up 1 pound, their body fat percentage goes up between 0.123% and 0.377%.